Much as we discussed the tangent problem and differential calculus, I want to also give you this little preview of what would be the second half of the course, the area problem and integral calculus. So the outcomes for this: describe the area problem and how it was solved by the integral. Explain how the idea of a limit is involved in solving the area problem, and recognize the total cost as the area under the marginal cost curve. So now we're going to look at another question from calculus. This is many quantities in physics, for example, quantities of work, may be interpreted as area under the curve. This leads us to ask the question, how can we find the area between the graph, like this curve here, and the x-axis down here? So one way to try to get the area under the curve is to break this up into smaller regions and then estimate the area based off of that. For example, break it into several rectangles of different heights, but with the same width. Now, there is an area in calculus when you may have variable widths, but we're going to talk about these consistent widths here in the beginning. So you can estimate it, and you can see some gaps down here, and there's some places it's over the curve, but it gives you a rough estimate. So estimation using rectangles. Here's a problem for us. Estimate the area between the x-axis and the graph of f of x equals x squared plus 1 over the interval from 0 to 3 by using 3 rectangles shown in the following figure. And here we go. So I've done a little bit of math for us already. Now, if you notice the height of the first one, the height is 1. The width is 1, so 1 times 1 is 1. For the second one, the height is 2. And the width is 1. 1 times 2 is 2. And then the third one, the height is 5. The width is 1, so 1 times 5 is 5. So this is 1 plus 2 plus 5, which is 8. So we can estimate this to be 8. Now, clearly there's some empty spots. So those empty spots mean these are areas that are not there, so we know it's more than the 8. Okay, this one is, sorry, a little bit different now. This one is where they're above. The other one they were below, so they basically took the lower edge of each interval. Now these take the upper part. So this first one, it has a height of 2 and the width of 1. So 1 times 2 is 2. The next one has a height of 5 and the width of 1. 1 times 5 is 5. And the next one has a height of 9 and the width of 1. So 1 times 9 is 9. We add that up, 2 plus 5 plus 9, and we get 16. So the actual area, we can see this exceeds the curve a bit. So the actual area is somewhere between, from up here, 8, and from down here, 16. So other aspects of calculus. So far we've studied functions of one variable only. Such functions can be represented visually using graphs in 2 dimensions. However, there's no good reason to restrict our investigation to 2 dimensions. Now, if you go into calculus 3, you get to do multivariate calculus, and so you're going to have you could have x, y, and z. And dealing with that, you'll have a 3-dimensional graph. It's pretty cool stuff. But for the sake of this class, we're focusing on the single variable calculus. And that's it for this little preview.